All right, and we are beginning our last unit of this semester, Unit 4. And the good news about Unit 4 is that there's really a lot of review. We're really coming back to several different ideas and tying those all together. All right, so a lot of review for you, a lot of concepts hopefully that you're very familiar with, all right, that surround systems of equations. And what is a system? That's what we're going to get to in just a minute. But to get you going, all right, we're going to do an opener here, and then standard for today is I can identify and verify a solution for a system of equations. And to do that, you have to be able to evaluate equations. And so that's why we have the opener we have today. So here's what I want you to do. All right, as soon as I finish talking, I want you to pause the video. All right, and I want you to evaluate this linear equation for x equals 1. I want you to evaluate this absolute value equation for x equals 1. And then tell me what you notice and what you think that might mean about the y values once you are finished. So go ahead, pause the videos, do those two problems, flip it back on, and we'll see how you did. All right. Okay, so hopefully you did this. Now let me throw my work up here real quick. All right, so what you hopefully noticed, all right, is that when you plug 1 in here, all right, and you go through your order of operations, all right, which we did a lot in our last unit, you get y equals 7. All right, and then what we talked about in the last unit is what that means is that the point 1, 7 is on that graph, okay? Now, go to part B here. Hopefully you plugged in 1 and you also got 7. Now, if you didn't, the most common mistake is that a lot of you probably got 15. And the reason you got 15 is because you forgot to take the absolute value of -2, all right, before you multiply. So remember, you have to take the absolute value of the number before you perform the operation with that number. So if you got 15, that's probably the reason. Now, if you go back and correct it, you also get y equals 7, which means that the point 1, 7 is also on the graph of this absolute value equation. So both of those y values are the same. And so what does that mean? It means that the point 1, 7 is in fact on both graphs. And so what does that mean when we talk about a system of equations? Well, if we were to graph both of these equations, what that means is that they would intersect at 1, 7. And that's what a solution is, all right? So all a system of equation is, if we go back down here, all right, a system of equations, let's write that word in here, is a set or collection of equations that you work with all at once. So for example, if we graph both of these equations, all right, they would intersect at 1, 7. So by working with both of those equations together, we create a system of equations, all right? Now, a solution to a system of equation is the point or points of intersection, all right, of the graphs for that system, all right? And there could be more than one intersection point depending on what types of functions we are graphing, all right? So what we're going to focus on today really is two things, all right? So the first thing is, all right, can I identify what a solution is graphically just looking at a picture, all right? Can I draw a graph with a certain type of solution, all right, which is kind of just looking at the same idea going in both directions. And then the last thing is can I verify, all right? And so if I verify a solution, all right, I'm going to say, hey, is the 0.17 a solution? And then we are going to plug it into the equations, and if it makes both the equations true, it is, in fact, a solution. All right, so let's flip to the next page and look at like types of solutions here. So we have 4 different types of solutions that we are going to see with our functions that we're going to work with. And we're really going to work with just the 3 functions, linear, absolute, and quadratic. So we're not going to work with exponential in this particular unit. All right, although we could have if we had wanted to. All right, so the first one here. So notice, all right, I have 2 lines that intersect once. So I have one solution. Now we could have other functions that intersect once and have one solution. So for example, right, I could have a quadratic and I could have a line, right? And then I get just one point of intersection. So the idea is that we get one point of intersection, okay? We could have 2 points of intersection, all right? So you can see that we have those 2 points of intersection here. I have a line and a quadratic that intersect twice, right? I could have a quadratic and a quadratic that intersect twice, right? I could have an absolute value and a quadratic that intersect twice. So the idea is that we could get 2 points of intersections, all right? Infinite solutions, all right? Now what this means, all right, is that basically, all right, we're graphing the same thing twice. So I think of this as like paving a road, right? So you pave it, you come back in, and then you repave it, all right? And what that means is that our equation is in just different forms, but once we graph them, all right, and we've seen that we have 3 different types of lines, right? And we could graph those and get the same graph. And then we could have no solution, which means the graphs don't intersect anywhere. All right, so let's just go through this real quick. all right, and have you just draw a couple of examples here. Now, once again, there's multiple ways to draw these, all right? So what I would like you to do is just pause the video and draw 1, 2, and 3 here, what you think would work, and flip it back on, compare that to what I'm going to do in just a moment, and we'll see where your understanding falls. Okay, so draw a system with a linear function and an absolute value function that has one solution. And once again, there's lots of ways to do this. So I might have an absolute value function like this, and I might have a really steep line right here, and they only intersect once there. You could have an absolute value function, right? And then maybe you had a horizontal line that intersects just at the vertex. All right, so the idea is that, right, we just want one point of intersection, right? And you need to make sure it's kind of where, even if it looks like the intersection might happen off the graph, right? We don't want that either, right? So you got to make sure you kind of have that right, all right, tilt to the line, right slope to the line. Okay, draw a system equation with a quadratic absolute value that has no solutions. All right, so maybe I'll draw a quadratic over here and an absolute value down here, right? Okay, so no solution right there. All right, they just don't cross. All right, draw a system of equations with a linear function and a quadratic function that has two solutions. All right, so I'll have a quadratic, maybe that opens down like that. I'll have a linear function that comes through like that. And once again, it's not what the graph looks like, it's the result of your graph. So hopefully you have two solutions no matter what you drew. All right, so that's really kind of the first part of the lesson. All right, okay, and now, all right, looking at graphs, right? So now we drew them. All right, now can you go the opposite way, right? Can you look at a graph, tell me how many solutions and what is a solution? So notice we have two lines here, and can you see that they intersect once, right? So how many solutions do we have? We have one solution because there's one point of intersection. And what is that solution? That solution is the point 1, 3. All right, if I look at the next one here, all right, how many solutions do we have? Well, we have 2 points of intersection, so we have 2 solutions. All right, and the first one is -2, 6. The second one is 1, 3. And the order doesn't matter. As long as you list both points, you're good. All right, notice our third graph here, right? How many points of intersection do we have? None, right? So there's no solutions, right? So what is the solution? There are no solutions, right? So there are none there as well. Now, notice the fourth graph. It looks like there's only one here, but this is a system, which means there's more than one. Well, if I only see one graph, that means it's graphed on top of each other, all right? And that means that we have infinitely many solutions, all right? Because we can pick any points that are on the graph, and that's going to be a solution. It's not all solutions because, like, this point doesn't work, all right? Okay, because it's not on the two graphs. But we have infinitely amount because there's an infinite amount on, all right, that graph. So infinitely many for both of those. All right, so that's kind of the visual part, all right, of our solutions to systems. Now, let's talk about more of the algebraic part, which is verifying our solutions, all right? So when we verify a solution, this really gets back into what we did in the opener, all right? And so if a point is on a line, when I plug that point in to an equation, it will make that equation true. And then if it makes both equations true, that means it's on both equation, it's a shared point, therefore it would be a point of intersection or a solution. So notice here the difference between the opener, all right, and what we're doing now is that it gives us the point, all right? And so what we have to know is that this is the x value and this is the y value. And then we have to put those into both equations and see what happens. So notice I'm going to take 5 and I'm going to plug that in for y in the first equation. And I'm going to take 0 and plug that in to x in the second equation. And now what I want to do is simplify the right side of that equation to see if I get a true statement. So 5 equals 2 times 0 is 0, and then 0 plus 5 is 5. All right, so 5 equals 5. That is a true statement, so I'm good to go. All right, so now I have to make sure it makes both the equations true. It has to be on both of them to be a solution. So now I'm going to take 5 and plug that in for y in this equation, and I'm going to plug 0 in for x in this equation, and do order of operations here. So -3 times 0 is 0. All right, and then 0 plus 5 is 5. So notice it makes both equations true, which means that point is on both equations. So these two lines intersect at 0, 5. So because it makes both equations true, this is a yes. All right, so now let's go to number 5. Is 2, 8 a solution to the system, all right, below? So once again, this is x, this is y. So I'm going to plug the 8 in for y. and I'm going to plug the 2 in for x. And then once again, we're going to just follow order of operations. So 2 plus 4 is 6. All right, do those grouping symbols first. Now, once again, take the absolute value of 6 before I perform any operations on it, and that is 6. And then notice I get 6 minus 1 here, which is 5. That definitely is not true, right? That is not a true statement. Okay, so we technically could stop there. All right, but I want to show you the other part, because notice if we had started with this equation, right, it would look like that 8 equals 4 times 2, and I notice I get 8 equals 8, which is a true statement. So notice we don't want one of each, right? We have to have two true statements. So if the first is false or the second is false or both are false, this would not be a solution. So it is not a solution. Okay, that is that. Okay, now let's jump down. So notice now in number 6, it says we have 2 points, R, 1, 2, and 5, 2 solutions, right? So we got too many R's in there. R, solutions to the system below. All right. Now, once again, we do this the same way, but it's like two separate problems. We're going to do 1, 2 first, and then reset and do 5, 2. All right. So once again, this is X, this is Y. So 2 goes in for Y, 1 goes in for X. All right. Grouping symbols first. So 1 minus 3 is -2. Then we have to do that exponent next. Now remember, -2 squared is -2 times -2, which gives us a +4. All right, and then 2 times 4 is 8. 8 minus 6 is 2. So it works for our first equation. So 1, 2 is on this quadratic graph. All right, now let's see if it's also in our absolute value graph. So I'm going to plug that 2 in for y, and then I'm going to plug the 1 in for x, and let's see what happens. All right, so once again, we have to start with those grouping symbols. So 1 minus 3 is -2. Now, once again, I have to take an absolute value before I perform any operations on that number, and the absolute value of -2 is +2. All right, and now when I multiply -3 halves times 2, I get -3, and then -3 plus 5 is 2. So notice 1, 2 makes both equations true. So 1, 2 is on both graphs. That would be one of their points of intersection. All right, so 1, 2 is a solution. All right, so here's what I want you to do. All right, I want you to do 5, 2, all right, and see if it's a solution. And that's where we're going to pick up in class, and we'll see what kind of work you have. So make sure you take 5, 2, determine if it's a solution for those two equations, and that's where we will pick up next time. See you then.